we are still talking about critical points in lesson 3. Okay, lesson 3 is officially the first derivative test. The first derivative test, which the first derivative tells us where the graph is increasing or decreasing. So find your critical points, and then testing is my derivative positive or negative in between those. Okay, now derivatives can be used to classify relative extrema as either relative minima, or relative maxima. As we begin to focus on analyzing functions, we can determine some predictable and specific behaviors for functions on our calculus journey through the mathematics of change. Okay, getting all philosophical here.
Wow.
Okay, this exploration here leads to the conditions and outcomes for the first derivative test. Use the graph of this function to answer the questions below. So, first of all, it suggests we use a red colored pencil. Circle all the points corresponding to the local maxima of f, not including endpoints. So, what do you see?
D.
Okay, we're going to talk about D. What else are we going to talk about? A. Okay, so the points on the function at A and D. Anything else? No. Okay, so let's fill in the blank. As I said, this part of the notes is kind of fun. State the x values where the local maxima of f occur, and that was when? X equals A and x equals D. At each maximum value, f changes from what to what? So as you approach a maximum value, what is your graph doing? And as you leave a maximum value, what is your graph doing? Don't think positive to negative. Not for, not for f, right? F changes from increasing to decreasing. Now, with that in mind, at each maximum value, f prime, so the derivative of f changes from what to what. And this is where we want to think positive and negative, because going into a max, you have a positive slope, yes? Coming out of a max, you have a negative slope. So it changes from positive to negative. What's the connection that we are making? We've already talked about this some. A positive first derivative indicates an increasing graph. A negative first derivative indicates a decreasing graph. Okay. Officially, it says to change colors. I don't care how you do this again, but use a blue colored pencil. Circle all the points corresponding to the local minima of f. Last time it was maxima, this time it's minima. Do not include endpoints. So, where would you like blue circles? C looks like a minima. Where else? C? Okay, I feel like you're stuttering. Okay, so state the x values where the local minima of f occurs.
I thought we included the endpoints.
No, not for what we're doing right now. Now, when we talk about extreme value theorem, and a graph being continuous and all that, we do, but not for what we're looking at right now. Okay, similar fill in the blank. At each minimum value, f changes from what to what? So as the function goes into a minimum and then goes out of a minimum, what's it doing? Yeah, it's decreasing into a minimum and increasing out of a minimum. At each minimum value, f prime, so the slope changes from what? Negative to positive. Okay. At each relative or local extreme value, the derivative f prime of x is either what or what? What is the derivative at these red or blue points?
0.
0 for, okay, there's the obvious answer, right?
Does not exist.
So here I'm going to say undefined because the derivative would be undefined there. Darn it. That didn't work. Seriously? I just want to finish the word. It will not let me finish the word. Gosh. Why? There we go. That's what you get. Okay, so we know, we've already talked, mins and maxes, horizontal tangent line, derivative is 0. Hard, sharp cusp points, derivative does not officially exist. We talk about the derivative being undefined. And so that's the idea there. So we could also say D and E does not exist. Next page is green.
Yay!
You know where the rulers are if you want one. I'm going to be going back and forth.
He doesn't need or pen.
You don't get a ruler.
Gosh, darn it.
My lines are straight.
Okay. Using a green colored pencil, sketch a tangent line, if possible, at the following points and determine their sign. And do notice it does say is possible. So at point B, wrong way. At point B. Okay, so there's point B. What's a tangent line to this going to look like? Okay, I'm going to go something like that. Ballpark figure, right? So at point B, my derivative looks like such. Or my tangent line. Now, let's fill it in. At point B, what do you know about the derivative of B? It is negative, right? Because what do we know about the slope of that tangent line? It is negative. Describe the change in behavior of the graph of f at this value. And this leads a little bit into what we'll talk about with second derivatives. But it's not a min, it's not a max. The graph isn't changing from increasing to decreasing. The graph is changing from being upside down to right side up. Or in other words, it's changing concavity. We're changing from concave down to concave up. So we're changing from where my graph is bold down to where my graph is bold up. Okay, we'll talk about that more in the next lesson when we talk about second derivative test, and that's going to be called an inflection point, or point of inflection. But for what's happening right here, my graph changes from concave down to concave up. So I know officially we haven't talked much at all about concavity, have we? I've thrown it in there when I feel like I need to a little bit, but I don't think it's come up in the notes before today. It will really come up in the notes in the next lesson, I think, because that's when we talk about second derivative tests. Okay, point D. We're going to draw a tangent line again. Where's D?
No.
No?
If I want to.
Don't want to? Okay. I can't really draw a tangent line here, can I? Okay. Notice it did say if possible, right?
Yeah.
This is a hard point, a cusp. You can't draw a tangent line, so let's go back to our blanks. At point D, the derivative at D is what? What'd you say?
Undefined.
You did not say undefined.
I said it.
Someone said it almost sounded like indivisible or
We
indivisible or
both
something.
said it at the same time. So
I don't know.
Messed
I heard something like indivisible or something. Maybe I'm hearing things. Could be too. Okay, so the derivative is undefined. Describe the change in the behavior of the graph at this particular value.
Cusp.
Okay, it's a cusp. What's my graph doing going into it? It is going up to it, so it's increasing and it's decreasing away from it, right?
Up cusp.
Huh?
Up cusp.
I'm just going to go with increasing, decreasing.
Yeah.
Okay, I was going to say, yeah. That's all I have here. I mean, I guess we could also, it says describe the change in behavior. I guess technically we could talk about, well, it's not a change though, because it's concave up on the left and it's concave up on the right. So the concavity doesn't really change there. Yes, increasing, decreasing. Okay, point E. See if we can draw a tangent line at point E. What's point E?
These pretty pointy.
Point E, right here. What's your tangent line look like? It is a horizontal tangent line. And go fill in your blanks when you're ready. At point E, the derivative of E is what? 0. Describe the change in behavior of the graph of f at this value. Well, can we talk about concavity again? To the left, my graph is facing, the curve is facing up. To the right, my curve is facing down. So it changes from concave up to concave down. So let's see. Derivative is 0, changing from, what did I say, concave up to concave down? Of these points, which two are inflection points? Okay, the two that changed concavity, right? An inflection point is when your graph changes concavity. And so at x equals b and x equals e. Okay. If a function f has a relative extrema at a point, then the derivative at that point is either 0 or undefined. Is the converse of this statement also true? So if there is an extrema, so if there is a min or a max, then the derivative at that point is either 0 or undefined. Okay, you're with that. Converse, is the converse true? First of all, do you remember what converse is? You switch the if and thens, right? So the converse is going to say, if the derivative at the point is either 0 or undefined, then there is a min or max at that point. Is the converse true? No. And what point here justifies that? Not a, okay, I guess I have the graph right here. Not a cusp. Because a cusp, the derivative is undefined, and there is a min or a max there. Yeah, the E here. Because what happened? The derivative is 0 or undefined, but was there a min or a max at that point? No. Okay? And so it was an inflection point, but not that case. So what point justifies your answer? And I'm going to say x equals E. Obviously, I'm going to write a little bit more than that. The derivative at E equals 0. But point E is not an extrema. Oops. Okay. If you want, you could say it is, I always say IP for inflection point, but I think more standard is POI, point of inflection. I don't know. Years ago I learned IP, but every time I listen to people teach calculus, I see POI now. Inflection point. Okay. Man, we have one more section to fill in the blank. Can we get to it? I don't know. Okay, let's see. We have a little bit of information of increasing and decreasing here. You guys have an idea of increasing and decreasing. Let's look at this real quick if we can. The graph is shown, defined from -3 to 7. List the open intervals over which the function is increasing, decreasing, or constant. So we talked about open intervals. I want x values. When is this increasing? From where to where? -3 to -1. And I think I just used interval notation. She might have used inequalities in hers. Okay. When are we decreasing? From 2 to 7. And in what interval are we constant? -1 to 2. Okay, those were easy to fill in. A word down here, I'll be honest, I was not familiar with this word, monotonic. Monotonic is a word that's mentioned down there, and that's when a function is, its first derivative does not change sign. So that means it's either always increasing or always decreasing is what your graph is doing. Okay, so we will pick up there tomorrow. I really don't feel like you're quite ready to talk about any homework.
That's what I like to eat. Good day.
I don't know. I guess I've only gotten through the first 8, but we haven't gotten to an example that will help us on the first 8. And I don't really know what else is past there.
Here, Miles.
So, you're always welcome to start looking at it, but
Miles.
we'll plan to hopefully try and get through the notes tomorrow.